So should we get started? You guys see my screen, right? So the lab today is about convolutional neural nets, and also we're going to make some synthetic data. So really don't have slides for it. It's more of the GitHub README. So it's linked to from the course website. So what we want to do is we want to use a simple convolutional network to recognize first EMNIST and then EMNIST characters, and then we want to construct a synthetic data set of EMNIST lines just to move us, closer to that sequence processing that we're going to do next week. So before you begin, make sure to do the lab setup, which I can do here in Colab. So it's that, setup where you git clone and then pip install PyTorch Lightning, and then you're able to run things. And if you are running on your own machine instead of Colab, which I actually am here, just make sure to git pull to get the latest changes. And you should now see this lab2 directory that you didn't previously have. So every week we release a lab. So the first thing I want to do is introduce us to EMNIST. So as you remember, MNIST is the digits. There's 10 digits handwritten, and that actually stands for mini NIST. And NIST is the National Institute of Standards and Technology. So mini NIST is mini because it only has digits, but the original NIST also had characters. So EMNIST is extended MNIST, which is like a repackaging of the original data set, which also contains the letters as well as the digits, but it's now in the EMNIST format that Jan LeCun kind of popularized. So there's papers with code about it, but we can take a look at the data in notebooks 01, look at EMNIST. So here's a tricky thing.
Can we pause for a setup question?
Yeah.
So for Colab, do people need to clone every single time for setup?
You do, yeah. Because every time you get a Colab, it's ephemeral. There's nothing on it.
But you save it to GitHub, though, right?
What's that?
You can save it to GitHub.
You can save the Colab to GitHub.
Yeah.
You can save it. You can save it to Google Drive, but I don't actually think it preserves the file system that you have. I might be wrong about it, but I don't think it preserves the file system. It takes just a couple of seconds to clone them. But the tricky thing about Colab is sorry, I have to find where I cloned it. Where did I clone it?
Yes, usually in content.
Oh yeah, content, there we go. So lab 2, there's the old text recognizer that we remember, the training, run experiment. So we remember these two. But now there's also notebooks, and there's 2 notebooks in it. Unfortunately, we can't run them as notebooks in Colab. So that sucks. What you can do is you can look at the notebooks in GitHub. So if you just want to follow along and look at them, you can just load them in GitHub, and that renders it quite nicely. Or you can set up, your own machine, and I'll actually share instructions on how to set up a Google Cloud Platform machine if you want to do that. But there's a trick with Google Cloud Platform, which is that if you sign up with your berkeley.edu email, you really won't be able to launch GPUs. Because, at least as far as I understand, all of us belong to the Berkeley kind of workspace, and that workspace has no quota for GPUs. And I don't know how to increase it because I don't know who's responsible at Berkeley. So if you sign up for Google Cloud Platform, sign up with your personal email. I'll share a document on how to do that later. But for now, I'll just actually show it in GitHub because I already ran the notebook and this is the output. So to look at the EMNIST data, we're going to import a new data module called EMNIST. So this is a new data class. So last week we only have the base data module and EMNIST. We now also have EMNIST, and then these are actually extra for next week, but we can look at EMNIST. So this is the EMNIST dataset. It has a mapping and then a split into train, val, and test. And if we look at, if we just instantiate it, call prepare data and setup. So this is the pattern for like all of our data modules. Prepare data, downloads data from somewhere, and then setup, splits it into train, val, test. And then print data, we just have a method. Where is it? Yeah, this dunder repr. That's like reproduce, right? This is if you overwrite this method on any Python class, then this is, you return a string from this method. That's the string that will get printed if you print the object. So that's what we do here. And we just print the number of classes. So now there's 83 classes. And I also print what the classes actually are, right? So there's 4 of these special tokens, which we'll talk about next week when we talk about sequence processing. But for now, let's ignore them. Then there's the EMNIST digits. Then there's uppercase letters. And then there's lowercase letters. And then additionally, I've added space, exclamation mark, quotation mark, hashtag, and all these different basic punctuation marks. So these are kind of for the future, but they're not part of EMNIST. What's part of EMNIST is just these classes, but we already include them in the mapping. It's just, there's not going to be examples of them. There's 260,000 images in train. Each image is of dimension 1 by 28 by 28. Why is there that extra 1? The reason is because it's the number of channels. So it's a grayscale image. There's only 1 channel. But for example, in ImageNet, this would be 3 because you would have red, green, and blue. So this is what PyTorch expects. So this is what we give it. And then around 60,000 validation, 60,000 test images. To get basically a batch of data, we can say, okay, data is our EMNIST class. Test data loader is a data loader that returns test data. If we wrap it in an iterator, then we can call next with it, and that'll return a single batch of data, basically. And then we can print the shape, the D type, data type, and then basically some statistics about this data. This is always useful to do just to make sure that your data is kind of what you expect. And it's like, I expect this to be a float between 0 and 1. And here, for example, the max is 1. If I saw that the max was 255 or something, then I would know that I probably forgot to, do some processing. So this looks good to me. 128 is the batch size by default. And so what we can do now is we can actually just print or plot rather some of these images, and the title of each subplot is going to be the label, right? So this is 9, this is L, 8, 1, 9, 7, capital Z, capital W, and this is supposed to be 2, but it really is going to be hard to recognize that as a 2, at least for me. Okay, and then what we can do now is we can actually train a base CNN model. And there's a couple of ways we can do it. We can do it in the notebook, and we can just import PyTorch Lightning, import our CNN model, which we'll take a look at in a second, and import our base lit model, instantiate the CNN model, instantiate the lit model with the CNN model, instantiate the trainer, give it a GPU, say it's going to train for like 5 epochs maximum, and then fit the lit model on the data. That will start training. It'll print, what the model looks like, and it'll eventually get to like 80% accuracy. If we train longer, it'll go higher, but whatever. And then we can actually ignore that. We can look at another random sample of data, and then this time we can both look at the correct label and also the predicted label. So the code for that is here. But basically by applying the model to the image, we get logits. By taking the argmax of the logits, we find the index of the class that has the highest activation. And then we can look up the label of that class in the mapping of the dataset, and we simply show it what it is. So on this set of test data, it's actually fully correct. So that kind of gives us confidence. So this is one way to train, but I really don't like training in the notebook. This is really just useful for sanity checking. But if we want to train in the way that we learned to last week, we can still, in Colab or on our computer in the terminal, run Python training run experiment, and then give it all the things that we care about as command line arguments. So one thing we care about is max epochs, GPU. Let's actually ignore that for now. The data class is going to be EMNIST. The model class is going to be CNN. So let's go and run this. So the first thing it does is it'll download the dataset. And this will also happen each time you launch a Colab. So that's another slightly annoying thing, but it's pretty fast. While it does that, we can take a look at our new model called CNN. So from last week, you might remember our MLP model, still here. Now we also have a CNN, and the CNN model is really a very Linnet-like model. There's going to be one conv block, another one, a max pool, and then a couple of fully connected layers. And the forward method is just apply the first conv block, apply the second conv block, apply a max pool, apply the dropout, flatten everything, apply fully connected, ReLU, and then another fully connected. So I said it's a conv block. So what's a conv block? I also defined that here. And so you'll notice this is also an NN module, just like the overall CNN is an NN module. And so this is really a powerful thing about how PyTorch is built, is that you can use what's basically a model as part of a different model, right? So this is like CNN is a bigger model of which some part of is a conv block, which is in itself a model, right? That has a forward method and an init method and everything. And this forward method is very simple. It just applies a conv and then applies a ReLU. Now we can look at how it's training. Looks like it's going pretty well. It's up to 79% accuracy. So one thing I mentioned in the README is this num workers argument. So that can really speed up training. And what it does is basically, we want the GPU to be as busy as possible. And the GPU is not busy while the data is getting loaded onto it, right? So each batch of data has to be loaded onto the GPU. While that's happening, the GPU is not processing. If to load a batch of data on the GPU requires processing of that data on the CPU, then actually, the GPU has to wait for the CPU to finish processing data, then put a batch on the GPU. By adding this num workers argument, we essentially start separate processes that are able to prefetch the data and preprocess it in separate CPU threads, such that there's always a queue of batches ready to be put on the GPU, so the GPU spends less time waiting. So that's a helpful flag to start adding, and you usually want to set it to the number of CPUs on your machine, which is like, I think, 4 on the Colab. And then another thing I want to talk about that's kind of useful is this overfit batches flag. And so if I give this to on the command line, if I use a float between 0 and 1, then it'll say like, only use this fraction of the data, only use that to in training, and then when you test, also test on that same set of data. If I say some number of integers like 2 or greater, then it's actually like this, like there's only 2 batches that will ever be trained on. And the reason this is useful is because you actually want to see your model overfit on just a limited number of batches, like 2 batches. Because if your model can't overfit on this limited amount of data, then it possibly can't represent the type of data that this is. So I'm going to put overfit batches 2, I'll put that num workers in there, and I'm actually going to boost the number of epochs, because each epoch is now going to be just these 2 batches. So it used to be 5, but I'm going to boost it over to 50, and let's see what happens. Okay, so it's learning pretty quickly. It's now getting to be 97% accurate, 98% accurate, 99% accurate. So I feel good that this model that we have is actually able to learn on this data because it's able to overfit to just a couple of batches. And Josh is going to talk more about this method of basically debugging neural networks in his lecture a few weeks from now. But it's something that you can start using, already. Okay, and then I'm going to explain what the homework is and then take questions after that. So the homework is in the cnn.py that we looked at. Let's look at it again. So there's our conf block, and there's our CNN architecture. So just edit it to improve it in some ways. So one thing you should definitely do is edit the conf block to be more of a ResNet block, right, as shown in this image from lecture. So right now it just does a conv and a ReLU. Can you make it do this like identity residual connection and another conv? And then part of the ResNet paper is actually a thing called batch norm. I didn't really talk about it, but if you want to add that, you're welcome to. You can take a look at the official ResNet PyTorch implementation for basically how to do it. We have a max pool in here. And as we covered with Josh, it's been falling out of favor in favor of a strided convolution. So you can try removing it and adding a strided convolution. There's some command line arguments for the conv dimension and the fully connected dimension. You can add more. And I think a really cool one to add would be, like right now there's 2 conf blocks. It'd be cool to add a command line argument for the number of conf blocks, right? And then dynamically create as many conf blocks as you requested on the command line. So if you do like a couple of these, then you just paste what you did in Gradescope, you explain what you did, and you'll get full credit for it. So the last thing I want to talk about today when it comes to the lab is making a synthetic data set. So we're looking at like single characters still, but we know that our goal is to be able to recognize whole paragraphs of text. So next week, we're going to take a step towards it and recognize lines of text, like recognize all the text within a line of text. And this week, we'll just make our data set for doing that. Okay, so it's in notebooks. Look at EMNIST lines. Let's go to notebooks. So we do our standard imports. This time we import a new data set called EMNIST lines. And the idea is that we want to be able to create basically lines like this. And part of what we need to do is first we need to generate sentences that are realistic, right? Because we're kind of working our way up to recognizing real English language handwriting. So the first thing we're going to do is we're going to synthetically generate English language sentences and then create, fake handwritten lines from them. So we made this thing called sentence generator. You can take a look at it. It's in data, sentence generator. It uses a data set called the Brown corpus, which is some English language collection of basically text. And we have like a pretty lightweight sampler of strings of text of some max length from it. So if I say sentence generator.generate max length 16, it will generate sentences of up to that length, but most of them will be shorter, right? So here's 4 that I got. And we can create an EMNIST lines data set using that. So what this data set is, it first loads EMNIST, the data set that we just looked at. And the mapping is the same as the EMNIST mapping. But it also has these parameters called max length. So that's the maximum number of characters in an image. Minimum overlap. So that's like minimum overlap between characters next to each other. And then max overlap. So that's like how much can they overlap, right? There's some code you're welcome to take a look at. But what it does is it basically generates things like this. So the first one, I say max length 16, max overlap 0. So that means there will be no overlap between characters. Each character will have its full width available to it. There's a special token P, which we use for padding. So our sentence generator, the max length is 16. The sentence it actually generates is going to be up to 16. So just to have inputs of equal size, we're going to pad the rest of it with this special padding token up to 16, right? So here are some sentences in the data set, and then here's what the input images look like. So it's literally sampling characters from EMNIST and then putting them next to each other. And this doesn't look so bad, but we can make it more difficult. We can say, okay, how about max length 34 characters, and then the characters can overlap by up to a third. So we can create that. And now it's starting to look more like, at least my handwriting, kind of like a very poor handwriting. That's going to be a challenge for our model. And we can make it more difficult yet. So take a look at this data set. There's no homework associated with it. It's something we're going to be using more next week, but I just wanted to introduce it this week. That is about it. That's all that's in the README. So I look forward what you guys do in the lab. Make it more of a ResNet from Lynette that it currently is. And I think that's it for labs.